Attention please, so we can make a start. So I'm pleased to introduce Dr. Martin Skov today, who will be talking about his Saltmarsh research. So to tell you something about Martin's background, for those of you that don't know, Martin used to be a boat builder, and he used to sail around the world in wooden ships while building ships, and lived in all kinds of strange places like the Faroe Islands. But then after some time doing that, he came to ocean sciences and did an undergraduate degree here. Something like 20 years ago, I suppose.
96 I finished.
Yeah. And then since then he's been working here, but also in quite a few other places before coming back here and well, starting lecturing. So please make start. Have you started the recording?
I've started the recording. Hello to everybody here and to those listening at home. Really pleased to be here. I worked out that it's probably about 6 years ago or something like that I gave another presentation to Ocean Sciences. I think we should do it a little bit more regularly than that, just to make sure that we know what each other are interested in. And I'm interested in coastal wetlands, and I suspect some people have sneaked into this room who might not know much about coastal wetlands. Salt marshes I'm going to be talking about today. Salt marshes are essentially intertidal habitats formed by vegetation, herbaceous grasses, fields. They are right on the coast, so they are very much exposed to all the coastal changes that we have at the moment, and as such they're really a good model system for understanding long-term changes and short-term changes and resilience of the coast, which is what I'm going to be talking about today. In salt marshes, as in many other coastal wetlands, there's been very, very strong emphasis on will they be able to keep pace in their growth, will sea level rise? Will they be able to accrete at the pace of sea level rise vertically? That's what I will call vertical resilience. And the field is more or less resolved now. There's still some controversy in there, but it seems to be that we are convinced now that marshes are fairly resilient to most situations of sea level rise. But in this period of really emphasizing this particular topic, another topic has been really under-emphasized, understudied, and that is lateral change in marshes. So sea level rise in response to that is mainly been attacked from a vertical accretion kind of perspective. And very few people have actually looked at what drives lateral changes, area changes in marshes, so area cover changes in marshes. And I want to start with this image here, which is Morecambe Bay. Google Earth the image of Morecambe Bay. So Morecambe Bay is a couple of hours north of here. It's about 30 miles across. And 6-7 years ago, I was part of a research consortium that worked on salt marshes, and we went to Morecambe Bay as part of it. And we had everything designed when we came there. We had Google Earth images of our marshes with GPS fixes for all our different sampling stations. And the first station we went to, the first marsh we went to, was Cartmel Sands. And when we arrived there, we found that it had expanded 300 meters since the last Google Earth image. And that was only 5 years ago. 300 meters for a marsh, which at that time, the Google image would have been probably about 600 meters wide. We're talking about massive change. We went around the corner to our next marsh, and that had eroded 60 meters in the same period. Across the bay, Carnforth Marsh was definitely in the process of eroding. Around the corner from there is a place called Silverdale. There used to be a really big salt marsh there, 1.5 kilometers or so, about a mile deep, gone over the last 20 years or so. Around the corner, Grange over Sands, that was built as a Victorian beach resort. There is now a salt marsh in front and a mudflat. There's no beach. What we're dealing with here is an incredibly dynamic system, and within the scale of a single bay like this, we have very opposite behaviors in change. Clearly very highly dynamic, and the questions that I started wondering was, or the things I started wondering about was, is this system resilient or not? Are there dynamics, natural dynamics, but the system overall is resilient or not? Or are we undergoing a period of change? What drives these shifts in lateral extent and cover of marshes? And what in fact regulates resilience of marshes to these changes? And by resilience I mean the ability to resist change, or to recover from change, or to adapt to change. What governs resilience? And so to enter into this topic, and I'm going to show you some research papers that we've done on this area over the last 5-6 years. I want to just explain to you a few principles about how marshes colonize first. What we have underpinning marsh colonization is a biophysical feedback loop. Much of what I'm interested in is these loops, these feedbacks between the physics and the biology. What happens is you get vegetation coming in and colonizing a bit of sand flat or mud flat. That causes water currents or wave energy to be diverted around that patch. As that happens, wave energy over the patch reduces. That causes opportunity for sedimentation to happen over the patch, and then so the patch can grow vertically and horizontally. And then that stimulates further colonization and further capture of sediment particles and further diversion away of water. And then you have a feedback, positive feedback loop there, and then the marsh can expand effectively through that. So that's a process that happens in marshes. The other thing I should explain to you is that marshes will not colonize everywhere in the intertidal, of course. These are plants that, in evolutionary terms, come from land, of course, so being further down in the intertidal is stressful. And there is a certain inundation level, certain level of flooding frequency that the plants cannot tolerate. And in the UK, that happens to be about mean high water of neap tides. That's really high up on the shore. This is in the top third of the shore or so. So marsh colonization is determined by flooding tolerance. And then if you have a shore gradient, a intertidal shore gradient like this, the marsh effectively can colonize the part of the shore gradient which is in that upper part, above that tolerance level. If you have a less steep shore, the marsh will be more extensive because there is a greater area to colonize now, and a less steep slope again, and we get a more expansive marsh. So in other words, the size of the marsh is very much governed by the intertidal, the shape of the intertidal foreshore, and that intertidal foreshore of course can be affected by erosion in turn, or by sediment accretion, sediment capture over time. And for that reason, sediment capture and what happens to sediment is very important dynamic in understanding what happens to marshes. It's quite easy to monitor what happens in marsh erosion directly in the field. You just have to go down to the bottom of the marsh and see what the shape of the marsh is, and here we have an erosion cliff and a marsh broken off. So it's quite easy to see. And erosion, when I'm talking about it now, and how that's affecting lateral extent, the area extent of marshes, we need to think about the bottom of the marsh really, where waves and currents will hit. And what prevents that erosion is partially linked up with the vegetation. The roots bind the sediments together, hold sediments together and prevent erosion. But sediment particle size itself is also a very influencing factor here. If we have clay, if this is clay here, clay is very resistant to erosion compared to sand. So a sandy environment is naturally more prone to erosion than a clay environment. So these are all factors that will affect the dynamics of marshes. I started to become interested in these patterns of marsh change, lateral change, and I started thinking about scales. So when you, if you wanted to understand what really governs marsh change, you could of course go and observe things on a patch scale. So when I'm talking about patch scale, I'm talking about anything that's a few meters or so in diameter. That's the kind of scale that we will do experiment on. And what governs changes in marshes on that scale might be very different from when we start looking at what governs total marsh area cover in the UK. I suspect very strongly that biological factors will be more important down here. Things like how much vegetation you have. Whereas up on this big scale, national scale, it must be big scale drivers like physics, climate that drive changes, long-term changes in the marshes. So that's kind of where I started thinking about these things. And then what am I trying to show here? Oh yeah, and then the temporal scale is of course important as well. If we imagine long time scales here along this x-axis here, very often what we study are the very, very short-term time scales, and we might have different behaviors which on a short time scale we cannot distinguish. This marsh system here is expanding, this one here is constant over time, even though it might erode a bit and then come back over time and erode a bit and come back over time. This one is declining. Management, by the way, operates at this tiny scale very often. They get very upset. People get very upset if their local marshes disappear. But understanding what's happening and managing a system really does require us to go to a bigger time scale. So I started thinking about these things. And then so here's some experiments that we've done, some papers that we published over the last few years. And I'm going to start off on a small scale and understand how biological factors and physics interact there. And I'm going to start with Mollie's just accepted paper in Journal of Applied Ecology. So Mollie is now Dr. Mollie Dugan-Edwards. She got her PhD this summer. And Mollie was interested in this process of marsh colonisation to patch formation, and then what causes this patch to merge with other patches next to it to form a more contiguous marsh and then expansion. And she figured from the literature that this ability to expand here, of course, will have something to do with wave forcing, so the amount of wave energy there is in the system. But it will also have something to do with the biology, especially density of plants. We know that more dense plant communities will trap more sediments, and then so that could positively stimulate the whole positive feedback loop that leads to expansion, the feedback loop that I mentioned earlier on. But there is another potential effect that could happen when plants stimulate this diversion of hydrological energy away around it, and that is the following. As you get this stimulation of the further colonisation, what can happen as well is that at some threshold in wave energy, the amount of energy that the patch generates at the side of the patch as it's diverting the energy around it, the amount of energy concentrated there might be so great that it starts causing erosion, scouring gullies around the patch, which then effectively prevents it from expanding laterally. We see this quite a lot in the marsh patches. So that might be created by density of vegetation. Too dense vegetation, if it's really dense, it will just act like a wall and divert the water very effectively. If, on the other hand, you have less dense vegetation, it might absorb some of that energy, and then you will not get that kind of scouring effect so much around the sides of it. And the other factor that will cause the scouring, of course, is if you increase wave energy, you just get more energy in the system, and then the prevention of the lateral expansion. So she experimented to try and understand how vegetation density and exposure interact with each other. So in Morecambe Bay, in the Red Wolf Bay, she selected 3 areas with different wave exposure. And inside these 3 areas, she planted out 3 type treatments of vegetation density: low density, medium density, and high density. And then she monitored change in accretion over time. So she had 4 posts around these patches, and periodically she put up these cross posts to measure down the elevation of the change in elevation of the sediment. She also did digital elevation models by taking 3D images like these and changing them to heat maps, so she could understand the actual volumetric changes in sediments around the patches. And this is what you found. And I'm going to walk you through this a bit slowly. What we have in the bottom here is sheltered conditions, moderately exposed conditions, and exposed conditions. And we're dealing with the net change in elevation of the patches over time. So positive values means accretion is building up. Negative values mean erosion. And if you look at the sheltered condition and the three different colors, being three different planting densities, planting density made no difference in a sheltered condition. If you go all the way up here to the exposed condition, what you now see is a clear effect of vegetation density. If you follow the red line here, you can see that the high density creates this hummock kind of type effect with erosion gullies around it, whereas the intermediate vegetation densities do not do that. The heat maps show the same. This is a heat map from the high vegetation density, where you can see this complete isolated patch formation, this hummock formation forming in the high exposure conditions. So basically we have an interaction between wave energy and plant density, which on the whole thing is summarized here in terms of shape. So as we're moving from low density and across to higher density and higher exposure, we end up with this hummock formation, which prevents lateral expansion. This is important to salt marsh representation especially, but it's also important to understanding why marshes in some conditions do not expand. They're just maintained in these patches. And if you go to Red Wolf Bay, you will see these patches all over the place and understand why this is happening. So summary of that is basically low wave conditions and any kind of the density we end up with emerging together, but when we're coming up in a high, we end up with these kind of patchiness and a prevention in the lateral expansion. So that's demonstrated to you how biology does have a controlling factor on these feedback loops with the physics on a small scale. I want to show you another example of how biology can have an effect on a small scale. And this is going to quite a different experiment. In this experiment, we just wanted to know whether biodiversity of vegetation will have any effect on marsh ability to resist erosion. So you will have heard of that biodiversity is has lots of influences on ecosystem processes across ecosystems. And we wanted to explore that kind of principle with vegetation biodiversity. And what we predicted was that if you get a mixture of plant species, you'll get plants in there which have got deep roots, shallow roots, fat roots, thin roots. You'll end up with a more holistic protection binding together of the sediment than if you only had one single species in there. And so erosion, the capacity for the marsh to resist erosion, to be more resilient to erosion, will be greater when you have more higher biodiversity. We tested that by just going out and taking cores of marsh and sediments around in two regions in the UK. And then we brought them back to the laboratory and put them in a flume, and we cut an opening in one side and eroded them under the flume. And then we measured weight loss basically over time, and that was the erodibility factor. And these are the results from that study. What you have here are two regions of the UK, Essex and Morecambe Bay. What you have in the x-axis is species richness. And what you can see is the erosion rate drops really rapidly as soon as you start getting more species inside your core. It's a very strong biodiversity effect on reducing erosion in the cores. The interesting bit about this plot as well is that if you notice the two bays, or the two regions in the UK, Essex and Morecambe, Essex has the same effect, but it's less pronounced. The effect of biodiversity is less pronounced. And the reason for this is that Essex is in clay conditions, whereas Morecambe Bay is in sandy condition. And so sandy substrates erode much quicker. And the take-home message for this is that biodiversity really makes a difference in an erosion-prone condition in particular. That's where biodiversity has the strongest influence on erosion protection by the community. So those are small-scale evidence of how biology really does affect the process of erosion and potentially expansion in salt marshes. I want to move to the medium scale now. And by medium scale, I mean estuaries on an Estuarine scale. So this is a paper that Kai led, who's my postdoc at the moment. He finished his PhD 2 years ago. He led this paper, and it's just been submitted to Landscape Ecology. And so if you remember for this Morecambe Bay situation, we had very different behaviors of the marshes around the bay. And Silverdale over here was studied quite extensively by one particular person at Lancaster University called Ada Pringle back in the 1970s or so. And Ada Pringle, about Silverdale, noticed from old aerial maps that if you went back to the 1930s, the tidal channel next to Silverdale was actually quite close in, and the marsh was quite small because of it. And then when she came back in the period she was working, she looked at where the channel was now, and it was further away, and then you had marsh, much bigger marsh. So she proposed that basically channel shifts shift the erosive forcing, and that determines whether marshes can expand or cannot expand. The closer the channel is, of course, the more erosion you get in the system. We wanted to look at that in much more detail, and we wanted to look at it. We looked at it in 3 estuaries in Wales, so that's the Duffy, the Mowdach, and the Durid. And inside each of these estuaries are a number of marshes. And this was a remote sensing GIS type study where we, to start with, we used aerial photography like this one, and then we eventually extended it back to use ordnance survey maps going back to the 1860s. So 150 years or so of change we looked at. And so in these aerial photographs, you can track where the channel is in the historical image, and you can mark where it is currently. So here, this situation, we've had a shift in the channel from being under the southern bank to being under the northern bank. You can see where the marsh is, and you can track where the marsh is now. So what's happened over this period with the channel shift is that as the channel shifted from one bank from the southern bank and now caused the erosion on the northern bank, the southern bank has actually expanded to compensate for this erosion. So you get some kind of a waxing and waning on the banks depending on where the marsh is, and that started making us think whether there was some kind of resilience in the system on that scale. So what Kai did was he mapped out the behavior in color here of these different marshes. So the black areas are areas where the marshes had been constant, they had not changed, they had not eroded, they had not expanded. The green areas are where we are seeing marsh expansion. Red is where marshes had been eroded over this 150-year period. And blue is where the marshes had been dynamic. That means that it had period of expansion, period of erosion, period of expansion, period of erosion over this time period. And so what you can see in here is that we actually have quite a lot of green expansion in our marshes in this region. But what we also have is, in blue, quite a lot of marshes which are dynamic. And so why are they dynamic? They are dynamic because of these channel shifts. So this image shows channel shifts in just one of these estuaries, and only from 1940s to the present. If we put the whole period in from the 1860s, you will not be able to see any detail. The channel shifts so often in this system, and it causes a shift in the erosional position, basically, an expansion and erosion around the marsh area. And so, where is erosion, these shifts more likely to happen in the estuary, is what this diagram is exploring. It's a little bit complex to understand, so I'll walk you through it first. What you have in the y-axis is how much of the estuary does a marsh typically occupy. So if you look at the Glaslyn estuary here, in the river end of the estuary versus the seaward end of the estuary, the marsh is quite wide. It occupies the majority of the width of the estuary, and there's only a small area left for the channel. And the relative dynamics of the channel is quite small, so the channel hasn't traveled very far across that estuary, it's quite narrow. If we now walk over to Maudach, and we look here, there's a situation in which the channel has migrated over a very big part, like 90% or so of the estuarine width, and as a consequence, the marsh is really narrow. And so you see these interrelationships, opposing relationships between how dynamic the channel is and how wide the marsh generally is in the system. And in the top end of the estuary, up by the river, the marsh tends to be wider, and at the bottom end of the estuary it tends to be narrower. And what it is, it's a bit like holding a snake by its tail. If you imagine the river end and you hold the snake by its tail up at the river end, and the snake does like that in the rest, and it does more of these swings in the bottom end of the estuary. That's what's causing these long-term shifts in the marshes. And if you, in terms of resilience, if you track what happens to the actual system in there, and we just focus on two marshes now on opposite banks, over time periods, we have periods where the northern bank marsh here has been eroding, but at the same time, the southern bank has been expanding. Shifts to another part of the century, and we have expansion in the northern bank and erosion on the southern bank. These are driven by these channel shifts. And what this implies is some level of potential resilience. In fact, what is happening on an estuarine scale is no net change. In fact, our estuaries, if anything, has been expanding slightly in the marsh area. So on an estuarine scale, marshes are, in this region at least, resilient to these channel shifts. And simply what happens is, when a channel shifts from one side to the estuary to the other, it just shifts the actual position of the erosion forcing, and then we can get cyclical periods like this, backwards and forwards. And one marsh might expand or then periodically erode, and another one might be doing the opposite, and then we get no net change in the system. We also wanted to understand what triggers these channel shifts, and we haven't been able to come up with an answer to that one. We looked at wind patterns. We can't find any link between wind patterns and these changes. We can't find any link between storminess and these changes, and we can't find any link between rainfall or river discharge and these changes in the marsh. Basically, what the actual trigger of these channel shifts, we do not currently know. I have some ideas, but that will be for the future to explore for sure. Okay, so that was at the intermediate scale. Of course, at that intermediate scale, this ability of the marsh to come back from erosion is influenced by biological factors, because it's the colonisation of the vegetation which enables the marsh to eventually expand, but it's the physical shift in the channel that really drives these periodic shifts in the area of individual marshes. We wanted to look at the large scale then next. And here's a study that Kai has just accepted in geophysical research letters. And in this particular study, we looked at across most of the UK. And what we did there, it was another GIS study, very similar approaches to the one done in West Wales, where we looked at maps and aerial photography going back to the 1860s. But the scale was much greater. We looked at 6 regions around the UK, Cardigan Bay, Morecambe Bay, Solway, Firth, Wash, Essex, Kent and Solent, and in 25 estuaries, more than 100 marshes, so about 40% of the UK marsh area, so quite a substantial study. And this essentially are the patterns of change in these marshes over time. What you have in all these little figures are different estuaries, or different regions, Solway, Morecambe Bay, etc. The blue lines shows the sum change in that region of the marshes, and the red lines are some of the individual marshes inside there. Overall, basically, this study showed that marshes in the UK, in fact, have been expanding. This was a bit surprising. That's not the picture that's been painted for quite a long time, I think, in the UK. Certainly not in the broader management domain. There was only one area of the UK where marshes have been eroding, and that's down in the southeast, in Essex, Kent, down here, down by London, effectively, down by the Thames. And that's where most marsh studies, incidentally, have been carried out. And in that region, we had erosion, but the rest of the UK, we have expansion, and in some areas, really very strong expansion. In areas like the Wash, which is over here, we have had quite strong, strange behavior, on the skin of it, quite strange behavior, but what this is human reclamation of land, so putting up a dike and reclaiming some of the marsh. But every time that has happened, the marsh has rebounded by expanding in front of the dike. So we still have the tendency for expansion in these areas. And so the question was why? Why do we get this change in behavior with erosion down in the south and expansion, in particular expansion as we're going up northwards? And so we looked at a range of different factors there, long-term data sets. These patterns were not driven by relative sea level rise. They were not due to changing patterns in weather, storminess, river flow, rainfall, temperature, precipitation, tidal range, and they were not due to the spread of a particular species of vegetation called Spartina anglica, which we know is a marsh builder. That was not the cause of these patterns. What was the cause was sediment supply. Sediment supply and fetch. So I have to take that a little bit apart. Sediment supply basically had a positive effect on marsh expansion, as you would expect. The more sedimentation that can come in, the more the elevation of the seabed can rise, the more opportunity for marsh expansion, effectively. And there's very rich sediment supply in our parts of the world, on the west coast and the north, and a relatively poor sediment supply in the southeast. The other thing that was positively stimulated or explained these patterns was fetch. So fetch is the distance of open water that you have in front of a coast or in front of a marsh. And fetch is an indication of wave energy. The bigger the stretch of open water, the more opportunity for wind to whip up wave energy. And so normally you would expect in marshes that fetch would be associated with erosion. So the more fetch you have, the more wave energy, the more erosion you should get in the marsh. But what you should remember here is that the wave energy we're talking about in salt marshes is relatively small. You know, we're talking about maybe 10 centimeters waves or 15 centimeters wave. We're not talking about massive waves generally on the scales of estuaries inside estuarine areas. And so what waves are actually doing instead is that they're resuspending sediments, putting them into suspension and pushing them up on marshes, pushing the sediment on the marshes. So again, these two things are showing the same thing. Sediment supply is what drives these patterns around the UK, which I'm sure some people in the room will be interested in, because we do not still know exactly what drives this sediment supply very well, or what the budgets are around the UK, but it's got very profound influences like this, and I'm sure it's not just on salt marshes, I'm sure it's generally on sedimentary systems around the UK. So that's a summary of it. Eroding down here because of poor sediment supply, and expanding up in the north because of greater sediments supply up there. I've got a couple of more experiments I want to just flag to you. And we're still operating now on the big scale. And so something I thought about a long time ago was marshes vary in how far they go down the shore. They vary across the UK in how much they go down the shore. So what we call the intertidal or downshore extent. So how far did they come down this gradient from the high water mark to the low water mark? It varies across the UK. Not just across the UK, it varies in fact across many regions in the world. In the US, East Coast, marshes are much further down there. This is an exaggeration. Marshes really around here, about here. In the US, they come all the way down here. In Canada, we've got similar patterns which might be associated with tidal ranges. In the UK, in the literature suggested that the east coast and the west coast somehow had different downshore extent of marshes. This, to us, we thought this is probably an indication of resilience, because the downshore extent surely must be an interaction between the ability of the biology, the sediment characteristics, etc., to resist wave erosion. So it must have something to do with how much wave energy is there. Maybe there's spatial variation in that across the UK. And maybe there's some spatial variation in sediment characteristics and plant characteristics, which gives rise to the resilience to erosion. So we wanted to look at that. And we went to the same regions as the previous studies, 6 regions around the UK. And inside these regions, we sampled an exposed salt marsh and a sheltered salt marsh to be able to unravel the effect of wave exposure on the patterns we got around. And then we measured the downshore extent. And this is effectively the patterns that we found. What you have in the y-axis here is how far down the shore a marsh reached. So the top of the graph here is the very high terrestrial fringe. And this is expressed in percentages. So 90 is effectively 10% down on the shore on the intertidal gradient that the marsh is. 60% it's got 40% down on the shore. But what you can see is a very strong north to south gradient in how far down the shoreline marshes actually reach. So up in Solway, further up in the north and in Morecambe Bay, they are literally only 10% down on the shore. They're really high up on the shore. When we go down to Kent, they are almost as far down as US marshes. Very strong difference across the UK. You can start thinking about what that will mean in terms of ecosystem services like providing habitat, feeding habitat to birds or fish or anything like that. We haven't even started looking at that. And so what drives this pattern? Wind forcing is the one that drives the UK scale pattern. Basically, we have a north-south gradient generally in the scales of the estuaries and the force of the winds. So the more wave height we have here, basically, the smaller the marsh is, the smaller the intertidal extent the marsh is. So wind force is the driver on the largest scale, on the UK scale. You move down one scale to talking about differences between regions and within regions, and then it's sediment characteristics that are important. So again, we're back to this thing about clay versus sand. So the more clay there is in a marsh, the more resistance it is to erosion, and the further down it extends onto the shore as a consequence. And finally, biology also has an effect. But biology really only has an effect when you move on relatively small scales and you move into the sandy marshes. And on that scale, in sandy areas, having more biomass, having more plants there, more root mass especially, causes marshes to be more resilient to erosion, and as a consequence they will extend further down. And another fact is the presence-absence of this Spartina plant, this pioneer species. If we have that pioneer species present, the marsh of course comes further down. That is the most tolerant species to inundation that we get in the UK. So biology is important there as well, on that scale, but mainly on that large scales, we're talking about physical factors being the driver. So putting it all together, UK-wide, waves being predominant drivers of this downshore extent. Regional scales, we're talking about sediment particles, particular types and characteristics, and then in sandy areas, vegetation characteristics being important on a smaller scale. Last thing I want to show you is almost all of the previous that I've shown has been observational studies where we used existing data sets and gone out and measured something else. We wanted to do some experiments to test for this resilience principles, and I thought I'd throw this photograph in here just to show that I actually do get out and do some things. And what we wanted to do here was directly measure resilience in the system by disturbing it. So basically what we did was we disturbed marsh patches and we saw how fast they recovered over time. And this was like a 1.5 year experiment, and we used the same 6 regions for that study. And we had 3 different treatments. The plots were relatively small, 30 by 30 centimeters or so. And in the worst removal treatment, we basically dug out the salt marsh plants and the sediment, and sifted it and put it back in again, the sediment, but without the plants. So we completely removed all the plants. In the second disturbance, we just cut the vegetation above ground. And the third one was the control, where we didn't do anything. And then we monitored the recovery of the vegetation over time, so the biomass coming back, and also the vertical accretion, so the growth vertically, which we measured basically by a couple of stakes in the ground and then coming back and measuring over time. We looked at a range of different factors and what explained the recovery rates across the UK. From physical parameters, wave exposure, stability of the sediment. We had some fancy equipment that we borrowed from the Netherlands that looks at how dynamic is the sediment. Does it erode? Does it come back and erode like this over time? The accretion, wave exposure, etc. And what we found as the driving factors here was sediment capture again, and temperature this time. So temperature was a new one. That one we hadn't had before. And so how does temperature really affect recovery here? Well, effectively, temperature acts on growth of the vegetation, the ability of the vegetation to grow back. The warmer it is, so in the south, the faster the level of recovery. So what we're seeing in this plot is basically what drives the rate of recovery, or the correlation of the rate of recovery, rather. And temperature is a very strong driver of this, along with sediment supply. And the south recovers faster than the north. So that seems like a bit of a contradiction to what I just presented to you early on, where I was telling you that the southeast is the least resilient part of the UK because sediment supply is low. Here we have a situation in which actually, if you disturb that vegetation, it recovers more quickly in the south than it does in the north. That seems to be contradictory. But actually it's not. There's a lot of text on here, don't worry, I'll walk you through it. It is not a contradiction. What it is a case of that you're mixing 2 timescales when you're looking at the resilience response. The disturbance experiment that I just showed you here shows that in the short term, marshes in the south are able to come back quick. But what Kai's long-term study shows that actually, ultimately, what's really driving the pattern is not short-term responses, which are affected by the biology, but are big-scale drivers like change in sediment supply. So you can have little short-term recovery, but it might be on a downward trajectory, the whole system. So in other words, what really is important when you talk about resilience here, and something that really hasn't been discussed in the literature, is scales of resilience. Temporal scale and physical scales interacting together. And so if we're moving and thinking about these 2 scales together and how they're affecting rates of recovery, on a very small spatial scale and small temporal scale, biology is going to be influential for sure. The growth rate of the vegetation, whether or not you have a nutrient-rich environment, etc. But when you come to the increasing scales up, increasingly it will be long-term, big-scale physical drivers like sea level rise, like sediment supply, like potentially climate, although temperature can affect both the biology and other factors long-term, the distribution of species. But physical factors basically increasingly taking over. This is not a revolutionary principle. I'm sure this is something that governs nature in general, but it's never really been established like this in a resilience context, and certainly not for marshes. Last thing I want to say is just that sediment supply has come up time and time again as being a crucial factor determining whether marshes are going to be able to keep pace with sea level rise or not. And this particular figure here illustrates that. It's a hypothetical, theoretical figure of how sediment support and sea level rise will interact with each other and enable marshes to persist into the future or not. We do not currently have data, empirical data on sediment supply from most places around the world. Yet it seems to be a really, really important factor, important driver of what happens to coastal sedimentary systems. Also, sediment supply is increasingly, we do know this, sediment supply is increasingly dropping globally. We're getting a less and less sediment supply into our coastal regions because of human activity, coastal protection, construction, dredging, or aggregates collection, etc. That might be a real problem in the future if you want to talk about resilience of our sedimentary coastal ecosystems like salt marshes. That's all I wanted to say. Thanks.
Thanks, Martin. Very interesting. Nice interdisciplinary work. Three.
Yes, great talk. Yeah, thanks. I didn't think it would be all about sediments today, but that's great. So the sediment supply, you say, is so critical, but of course you can only supply the sediment when you have the hydrodynamic forces to bring them there, so surely they're linked as well. And I was also wondering, what's the link then between the Spartina and the sediment properties? So are they more happy in clay, silty environments or sandy environments? Because again, that will be a feedback mechanism there to consider, because they're not going to be independent, are they? The vegetation and the sediment?
No, they will be linked to each other, but big scale geological, on a bigger scale, there are differences in the characteristics of sediments feeding into an area, right? So generally vegetation, if you get to really high clay content, it's difficult for them to establish very well, because to push the roots through a very dense sediment can be really tough. On the other hand, sorry?
But that's not a resistant
yeah.
soil in its own time.
That's right, but on the other hand, once it's anchored in there, it takes a lot for it to get out. I don't know what the exact answer is to that question, but yeah. Yeah, I think the recovery rate, if you had the same temperature, I expect it to be much faster. If you had the same temperature, same in everything, and you did it in sandy and you did it in the clay, I expect it to be faster in sandy than it is in clay.
It would be easily done by empirical.
Yeah, you could do that, definitely, yeah. Yeah, cool.
Yeah, great talk, Martin. I really enjoyed that. Can you say a little bit more about the human factor? Because, just give an example, the estuaries in West Wales you looked at are more pristine than the estuaries in the southeast, perhaps. So did you look into the human factor?
No, I haven't gone around and looked at the actual values for changes in sediment supply around the place, but there aren't that many studies, so let's try to look at that on a bigger scale, as you probably know. So yeah, I don't know the exact details of that, no. Right?
Just in a sense, kind of following on from that, from a river water quality management perspective, avoiding excessive agricultural disturbance of land and erosion from the land is a major issue. So is it possible that the salt marshes we see are a testament to land use practices over 200 years that are now actively being discouraged because of their broader environmental impacts within the riverine environment, and that actually widespread salt marshes are a non-natural for them. And actually their erosion might actually be a reflection of improving river qualities and things like that, and better land use, better land management.
Yeah, so sediment suppliers, suppliers have been showing is a really important factor because it changes the elevation of the shore, and there are places around the world where that's been, what you're talking about there, has been demonstrated really well, where, like in the US Eastport, for instance, historically the marshes were nowhere near as extensive as they are now. Since human influence and use of land, it's just, you know, the actual input of sediments have been so much greater. And this has happened also in Southeastern Asia. So this has definitely happened. So you could have potentially a rebound. And here in Wales, we are wondering about whether that would have been happening. You know, forest change ultimately coming in with grazing pressure, etc. So it's possible, but I think in some of these things have been stabilized for a very long time. The agricultural environment, relatively stable from a sedimentary input kind of type perspective.
It's not that long ago, things like on the Saltmarshes, they were actively letting flooding into the land.
Yeah.
Now it's gone the other way, so there have been some very substantial changes in managed sediment supply.
Yeah, no, and I think the question that you're asking is really also to do with what science scales should be looking at. So the European, I should say it's differently in these Brexit times. A lot of management that we have in the natural environment in the UK is governed by something called Natura 2000, which is basically an agreement made across Europe to conserve what we have or to recover what was there in the past. I think that some of these are a bit artificial. Some of these, it's like, so we must have a certain kind of percentage area covered by certain systems. But that neglects this possibility of long-term changes in our ecosystems. We're investing a lot of money around the place in restoration of some systems which really, if you look at the longer-term scale, they might be on a downward trajectory and there's nothing you can do to stop that loss, and it's just a natural process, perhaps.
Are you measuring sediment supply?
We have not measured sediment supply, so this is a stumbling block in this whole field. Measuring sediment supply is a whole different. Oh yeah, so the sediment supply in the big scale study was derived from modelling, basically. We have some areas where we have information for, but if you want to operate at that scale, you have to go to modelling. And we have explored different types of models. There are some really well-established ones. There are ones where you just go by characteristics of the estuarine environment, the hydrology, the depth, the width, that sort of stuff. And then there's also approaches where you simply look at the vegetated to the unvegetated area, which seems to be like a circular kind of argument. But actually it's proven to be a very good predictor as well.
But how do you, so if you measure it locally, how do you measure it?
That you have to ask Jaco down there, but yeah, you can do it in different ways, but you need some sophisticated equipment generally if you want to do it over. And this is constrained to very small scales, isn't it, Jaco, because it's so expensive.
Yeah,
so
we have been doing it, or Colin has been doing it in the Saltmarshes for the last 50 years. And,
but once a year, right?
Once a year.
Yeah.
So that's on a longer time scale and on a much larger spatial scale.
So some of these things you're very constrained by because you can only do periodic observations with it, and you can only do spot observations. If you want to do these kind of scales, that's a major investment. So at the moment, it seems to me that this sedimentary field, when you're looking at big budgets and stuff, is done by modelling, isn't it?
Mainly.
Yeah. Martin is not saying anything.
Tim?
You showed that on the large scale, climate is a key driver of salt marshes. There's studies over 160 years show on a UK scale, salt marshes are expanding. Would you say that climate change benefits salt
marshes? That's a good question. It's a convoluted one to answer because what you have is that, like everywhere, all other systems, you have a polar migration of species, right? And so in the Arctic, the species which are there tend to be less vigorous growing, and so what is happening is a northward shift of the more vigorous growing species. So you probably will get an expansion into the Arctic. for sure. But in the other end, when you go down to the subtropical kind of realm, what's happening there is that you're getting mangroves shifting north, and they're taking away the habitat from salt marshes, effectively. So I don't know what the net effect is.
Gareth?
Oh.
I want to steal a student question. Yeah. I was just wondering, so this graph, Martin, reminds me of this sort of binary view of ecosystems, right? This is on the y-axis either salt marshes being there or not being there. It reminds me of sea level rise and tropical coral reef islands, and this idea that once islands are either there or they're not there, and then once they're not there, that's bad for people, right? Because
Yeah.
drown, and there's nowhere to live. But I've often thought that there must be an interim period where other services and functions vanish between that binary response of being there and not. And I reckon that must be true for tropical islands. So I was wondering whether anyone's thought about that, whether you had any ideas on that for salt marsh.
When you start going to this, how ecosystem services are affected by these changes, and especially by these long-term changes and the waxing and the waning of the system, it's extremely poor, the knowledge about really how that affects ecosystem services that I know of, anyway. And this period that you're talking about is when you're getting close to the threshold, so you're getting this kind of critical slowing down type happening there. And I think something like that could be potentially happening in ecosystem services, but God knows, some of them might be increasing and some of them might be decreasing at that particular period.
The threshold, right? There might just be aspects of the system we're not measuring that might vanish long before.
Yeah, that's true.
Approaches that threshold. It may be that that's occurring in salt marshes all over the UK. It's just that they're still there.
Yeah.
But their intrinsic sort of, what's the word, their quality
Yeah.
has dropped. And
Yeah.
So is anyone sort of trying to quantify that?
No.
And I wonder how much that's actually going on with ecosystems with things like this. And
Yeah.
we're not capturing that.
Yeah.
Okay, we're going to do one last question. Did you have a question?
When you look at different estuaries, does any measurements on pollution in the water at the time? Does it went through a more heavy period, there might be more pollution. Then if you went through more agricultural pollution, might plant more fertilizer into the ground. So this one might have helped promote
Yeah.
growth.
That's correct. Pollution could have an effect. In fact, there's quite a lot of genetic factors that could have an effect on the patterns. I think within the gradients you're dealing with in the UK, I don't think pollution will be a major factor in the UK, but there's definitely other places around the world where it definitely can be. And I mean, some places in Southeast Asia, the nutrification of the water would have boosted marshes significantly in some areas.
Okay, thank you very much. So if you've got any more questions,